Okay, let's unpack this. Today, we're embarking on a truly fascinating deep dive, spanning centuries and disciplines, all from a stack of sources that might, at first glance, seem wildly diverse.
Hmm.
We have everything from ancient Roman architectural treatises to 16th century mining practices, and from the intricacies of modern construction management to the philosophy of systems thinking.
Quite a range.
Exactly. Our mission, to connect these seemingly disparate dots, extract the most important nuggets of knowledge, and show you how deeply intertwined our built world, its history, and its future really are.
Yeah.
Think of it as a shortcut to being well-informed about the surprising foundations and modern innovations that shape our environment, with plenty of aha moments along the way.
And what's fascinating here is that even with such a broad array of material, you see these consistent themes emerge: the evolution of human ingenuity in building, the ongoing quest for efficiency, and the critical thinking required to manage complexity. We'll be looking not just at what was built or done, but why it mattered and how those historical principles continue to resonate in contemporary challenges. This deep dive will highlight how understanding these different facets can give us a truly holistic view of progress and human endeavor.
Absolutely.
And today, we have a particularly intriguing thread to follow: how a 19th century French architect, Eugène Viollet-le-Duc, an ardent student of medieval cathedrals, became this unlikely hero for 20th century modernists.
That sounds fascinating. Not just copying style.
No, not at all. He wasn't just interested in copying Gothic style, but in dissecting its underlying structural logic, celebrating it as a kind of proto-modern skeletal frame.
Wow.
It's a powerful lesson in learning from history, not by copying its style, but by understanding its logic, which laid the groundwork for modernism's rejection of mere applied ornament.
Okay, so let's start there, maybe stepping back even further first. Our sources offer a fascinating glimpse into the very origins of architectural thought, contrasting the Greeks and the Romans. What fundamental differences in their foundational logic emerged, and how did those distinctions influence everything that came after?
That's a crucial distinction, yeah. The difference between Greek and Roman approaches to architectural orders is absolutely foundational to understanding subsequent developments and, well, to the very debate that architects like Viollet-le-Duc would later champion.
Okay.
The Greeks, as sources like Kostoff and Viollet-le-Duc's lectures on architecture tell us, saw their architectural orders, whether Doric or Ionic, as the very structure itself.
The structure itself.
Yes, it wasn't just decoration, it was integral. You literally couldn't strip a Greek building of its principal ornamentation without fundamentally compromising or even, destroying the building. There was an essential unity of structure and appearance, where the form was most appropriate to its function. Viollet-le-Duc described this as a delicate faculty for observing moral and physical phenomena, almost an intuitive science, leading to most perfect productions of science. Their orders were the building's logic made visible.
So a Greek column wasn't just a pretty facade. It was a crucial load-bearing element, and its fluting or capital directly expressed that structural role. That makes incredible sense.
Exactly.
But the Romans, well, they had different priorities, right? Monumental scale, practical results. They really diverged from that, didn't they? What were the fundamental philosophical or maybe pragmatic differences in their architectural mindset?
They absolutely did diverge. The Romans, driven by what Viollet-le-Duc calls a thoroughly practical spirit, often viewed Greek orders primarily as decoration.
Just decoration.
Pretty much. For them, an order might be removed, omitted, displaced, or replaced by something else, without the structure being thereby seriously affected. This reveals a fundamental philosophical divergence. The Romans were masters of the arch and the lintel, often using these opposite principles in the same building without fully harmonizing them, as Viollet-le-Duc observed. Their priorities were grand scale and monumental impact, rather than the Greek ideal of integrated form and structural truth.
Right.
You see this in their widespread use of engaged orders, columns that were embedded into the wall, serving both as buttressing and decoration, like on the exterior of the Theater of Marcellus or the Colosseum.
Ah, okay, I can picture that.
While the Greeks did use engaged orders sometimes, like in the Temple of the Giants at Agrigentum, they never superimposed them in that multi-story, purely decorative Roman fashion. This early divergence between architecture that directly expresses its structural integrity and one that prioritizes monumental scale and applied decoration isn't just a historical footnote. It's the foundational debate that architects like Viollet-le-Duc, centuries later, would fiercely engage with. He was effectively drawing a line in the sand for what honest architecture truly means, a line that still shapes contemporary design discussions around authenticity and sustainability.
That's a great point. Okay, so looking forward, about a millennium from the classical world, the Middle Ages brought about some incredibly sophisticated structural solutions, particularly with Gothic architecture.
Yes.
Forget arbitrary decoration. This was about pure, rational logic in stone. And it's here that the work of Viollet-le-Duc really shines a light on how we understand these structures, almost framing them as prototypes for modern engineering.
Right, and this raises that important question. How did medieval builders, without our modern engineering tools, achieve such soaring, intricate structures?
How do they do it?
Our sources, particularly Viollet-le-Duc, suggest a fundamental shift towards rational methods over mere tradition, especially evident in 13th century architecture. He highlights that in this period, it's impossible to separate the form from its structure. Every member of this architecture is the result of a necessity of that structure.
Impossible to separate.
Exactly. This is a critical concept, and indeed, it's one of his most profound contributions to architectural theory, making him a hero to later modernists.
Yeah.
He saw Gothic architecture not as a style to be copied, but as a dynamic system of forces and counterforces, a skeletal frame that directly expressed its structural integrity and efficiency. He argued this was a triumph of engineering logic, not just aesthetics.
So he wasn't just a romantic looking back at old buildings. He was an analyst, almost like an engineer, trying to understand the why behind the what.
Precisely.
This idea of structural honesty, where a building's appearance reveals how it's built, feels incredibly proto-modern. It's a powerful connection between ancient ingenuity and future innovation.
That's precisely his genius. Viollet-le-Duc described 13th century architecture as real architecture, applicable to all purposes precisely because its principles proceed rather from a course of reasoning than from a form.
Reasoning over form.
Yes. For these architects, form never shackled them because it followed function and structure. He passionately argued that you cannot remove decorative forms from an edifice of the 13th century or attach any to it without detriment to its solidity, its very organism.
Like a living thing.
Exactly. He famously compared it to the natural world, saying, as in the vegetable and the animal kingdom, there is not a form or a process that is not produced by a necessity of the organism.
Oh.
This meticulous, rational analysis of Gothic structures, their rib vaults and flying buttresses, as an efficient, honest structural system rather than just an aesthetic, deeply resonated with 20th century modernists. They were seeking a similar rejection of superficial ornament in favor of a truthful expression of materials and structure.
Makes sense.
His writings effectively traced how looking deeply into the past revealed principles for the future.
That's a powerful analogy, comparing architecture to a living organism where every part has a purpose. And it explains how they broke free from earlier constraints, like the Roman rules, allowing for incredibly innovative spatial solutions.
Indeed, medieval architects made significant vaulting advancements. They ingeniously used two portions of arcs for transverse and wall ribs, a method that allowed them to vault every plan, whether drawn on a parallelogram, a quadrilateral, a triangle, a regular or irregular octagon.
So much more flexibility.
Huge flexibility. This was a revolutionary departure, freeing them from the rigid, often rectangular rules that had constrained Roman and Romanesque architects. This innovation opened up possibilities for endless developments in design and interior space.
Right.
Something that an architect like Antoni Gaudi would later take to extraordinary extremes in his own structural explorations, directly influenced by Viollet-le-Duc's rationalist approach.
Oh, Gaudi, okay.
Even the seemingly decorative integration of design elements, like the two towers on Notre Dame's facade, shows this deep reasoning. The architect connected them with a lofty open gallery which relieved the abruptness of the transition from the solid to the open, making the facade a homogeneous whole. It was all part of a cohesive structural and visual system.
And it sounds like this dedication to structural honesty and rational method extended to the craftsmanship itself, emphasizing not just what was built, but how it was built.
It absolutely did, and Viollet-le-Duc actually lamented the decline in workmanship that began with the Renaissance, drawing a stark contrast.
Oh, interesting.
He noted that during the Middle Ages, masters gave full-size diagrams for construction, moldings, and ornaments, ensuring each stone was finished, molded, and sculptured before being laid.
Finished before being laid.
Yes. This method had the immense advantage of forming skillful and intelligent masons and excellent stone dressers because they had to fully understand the piece of work and its structural role.
Right, they had to know the whole picture.
Exactly. This practice declined with the Renaissance, when ornament began to be cut in place on roughly shaped stone, leading to a total want of harmony between the jointing and the architectural feature. The mason's function became degraded, and with it, the crucial principle of integrating structure and form was diminished. This historical observation by Viollet-le-Duc underlines his core argument that the logic of construction, evident in Gothic structures, was a profound and lost wisdom that needed to be re-examined.
Not just for history buffs.
No, not just for historical appreciation, but for its enduring principles relevant to future architecture. His writings effectively traced how looking deeply into the past revealed principles for the future, inspiring a generation of architects to seek structural truth in their own designs.
Okay, so from the pure structural logic of the Gothic, we swing to the Renaissance. Architects like Andrea Palladio looked back to antiquity, but with a profoundly different lens. He was deeply impressed by Roman ruins, but as our sources put it, like most lovers, he saw only what and how he wanted.
Ah, that's a great quote.
It is, isn't it? This selective admiration led to a truly influential, yet sometimes irrational approach that stands in stark contrast to the Gothic rationalism and structural honesty championed by Viollet-le-Duc.
Yeah, this is where we really see the cyclical nature of architectural development and the fascinating ways architects interpret history to serve their own visions. Palladio, deeply influenced by Alberti's De Re Edificatoria and Vitruvius's 10 books on architecture.
The only surviving Roman architectural text, right?
That's the one. The only preserved architectural book from the Roman and Greek world. He developed a highly systematic approach based on these. His Palladianism wasn't just about copying antiquity. It was built on the conviction that a universal architectural vocabulary was desirable and possible, a vocabulary developed by the ancient Romans.
A universal language of building.
Sort of. He believed that careful study and judicious use of these forms would lead to beauty. This beauty, for Palladio, was rooted in historical correctness, and it includes the most practical, reasonable solution of a specific problem on hand.
So he was trying to create a systematic, almost universal language for building, drawing directly from the classical past, but perhaps filtering it through his own interpretation of what that past should be, rather than its pure structural essence.
Exactly. Our sources, particularly Ackermann's analysis, note that his trip to Rome in 1554 and contact with Michelangelo, along with Venetian patronage, transformed him from a theoretical classicist into a more encompassing and sensitive designer who surpassed proportion and Vitruvian decorum to attain a profound and sensuous style.
A sensuous style.
Yes, but this style could also be quite pictorial rather than tectonical, meaning he sometimes used classical elements for their visual applied effect rather than for their strict structural logic.
Ah, okay. Applied effect. That's the key difference then compared to Viollet-le-Duc's focus.
It's a key distinction, yes. Palladio admired temple porticos and would apply them onto villas or fragment them and integrate pieces onto churches, sometimes using the orders like brushstrokes on his late Byzantine facades. It was about visual harmony and proportion, not necessarily the overt expression of load and support.
That's a fascinating insight into how historical influences can be reinterpreted. Can you give us a concrete example of this blend of classical inspiration and this new, sensuous, sometimes pictorial application?
Certainly. Consider the Palazzo Valmarana in Vicenza. Its facade is one of Palladio's most effective responses to narrow urban streets, conceived in planes rather than purely sculptural terms.
Okay.
The giant pilasters, being planar, integrate well with neighboring facades and were likely suggested by Michelangelo's St. Peter's model. What's intriguing is the abrupt shift of scale in the end bays, where the giant order is seemingly abandoned. This was executed with an irony learned from Mannerists like Giulio Romano, who enjoyed playing architectural jokes on the purists. This highlights Palladio's willingness to manipulate classical forms for aesthetic or expressive effect, rather than adhering strictly to a rigid, purely structural truth.
Almost like visual puns in architecture.
Kind of, yeah. Another compelling example is his design for the Church of Il Redentore in Venice. Here, Palladio had to accommodate three distinct ecclesiastical functions: monastic, votive, and congregational.
A complex brief.
Very. His solution involved clearly separating these parts with a great tribune, nave, and choir, using columnar screens to allow light and sound to pass without compromising privacy. Our sources note that this design likely reminded him of his intensive studies of imperial baths.
Roman baths.
Exactly. Where he reconstructed sequences of independent spaces, sometimes visually connected through similar columnar screens. He associated the problem of joining a rectangular nave to a central plan tribune and choir with that of linking thermal shapes and functions in a similar series: frigidarium, tepidarium, and calidarium.
That's brilliant, connecting those ideas across building types.
It showcases his genius in adapting classical principles to new problems, but also his freedom in interpreting and transforming those principles, sometimes prioritizing visual impact or functional division over a singular, overt structural expression. And that's a stark contrast to the purely rational forms that Viollet-le-Duc would later celebrate.
Okay, we've journeyed through centuries of architectural philosophy, from the structural honesty of the Greeks to Viollet-le-Duc's rational analysis of Gothic cathedrals. But these grand statements aren't built in a vacuum, right?
Not at all.
They are, at their core, a testament to humanity's evolving mastery of materials. So from the abstract principles, let's zoom in on the fundamental building blocks themselves.
That's an excellent way to transition, because what these diverse examples reveal is a constant, evolving dialogue between human ambition and material constraints. Each material, with its unique strengths and weaknesses, isn't just a building block, it's a co-creator.
A co-creator. I like that.
It dictates the possibilities and pushes us towards ever more sophisticated engineering, proving that limitations often spark the greatest innovations. Our sources highlight the incredible variety that humanity has utilized throughout history, from the most basic to the highly sophisticated.
Like what?
Early houses, for instance, were constructed from readily available materials like mud, poles, brushwood, grass, and loose stones, leading to an astonishing 32 basic forms for house alone, as Kostov tells us.
32 basic forms. Just for mud and sticks.
Pretty much, yeah, with diverse plans and roof profiles adapted purely empirically to local conditions.
That's a staggering variety just for early houses, showcasing incredible ingenuity. And this empirical understanding evolved into more systematic knowledge, even in areas beyond typical building construction, like mining.
Absolutely. One of our fascinating sources, Agricola's De Re Metallica from 1556, gives us incredibly detailed descriptions of 16th century mining techniques. It's a testament to early engineering challenges and their sophisticated solutions, demonstrating a systematic approach to overcoming material limitations.
So what kind of techniques are we talking about?
Well, for example, he meticulously describes the timbering of shafts using uprights, cross timbers, stakes, and posts to prevent collapses in unstable earth.
Critical stuff.
Absolutely critical. He details various pumping mechanisms, from human-powered windlasses with winding ropes and buckets to horse-powered machines with toothed wheels and drums, and even water-powered pumps to combat flooding in deep shafts.
And ventilation. That must have been a huge issue.
Massive. Achieved through complex bellows systems, some designed to supply fresh air and others to actively suction heavy and pestilential vapors out of deep shafts up to 120 feet deep. An impressive feat for the era.
It's incredible to imagine these operations in the 16th century. What does this level of ingenuity in mining tell us about the foundational, unspoken challenges that defined early human engineering, long before terms like systems thinking even existed?
It tells us that the core problems of engineering, understanding materials, managing forces, and creating viable systems are ancient. Agricola provides intricate metallurgical processes, too, like cupellation for refining gold with lead and the use of various fluxes to help ores melt and separate slag.
Fluxes, what are those?
Substances that help things melt. These included surprising compounds for the time, like saltpeter, litharge, a lead ash byproduct, argol from winemaking, and glasgol, essentially potent chemical agents that demonstrate a sophisticated, albeit empirical, understanding of material science centuries ago.
Wow. Okay, back to more common building materials. What about wood?
Our sources delve into wood properties, noting that longitudinal shrinkage is negligible, but tangential and radial shrinkage are significant. This is why a sausage skin bursts longitudinally when the filling expands, not circumferentially.
Wait, a sausage skin?
Yeah, the circumferential stress is twice the longitudinal stress, as Gordon explains in his work on materials.
Okay, that sausage analogy really makes the concept of stress distribution stick.
Doesn't it? An interlocked grain in wood, resulting from repeated cycles of spiral growth, makes it incredibly hard to split, a natural engineering marvel.
Amazing. What about masonry and concrete, which are so fundamental to much of our built environment?
For masonry, mortar is highlighted as equally important as the units themselves. It cushions, seals, bonds, and affects the appearance. Modern mortar typically combines Portland cement, the primary bonding agent, with hydrated lime for workability along with sand and water.
And before Portland cement.
Historically, before the late 19th century advent of Portland cement, lime was the main bonding agent, hardening slowly by absorbing carbon dioxide from the air.
Slow process.
Very. We also learn about cinder concrete blocks, which are lighter and offer better nail-holding power, but require thorough curing before installation to prevent expansion and contraction issues.
Right. Gotta let them cure properly.
And underpinning everything, literally, are foundations. Every building needs one to transfer loads to the ground, and their design is a specialized field accounting for highly variable soil, rock, and water conditions, profoundly impacting costs and structural systems. This detailed look at materials, from ancient mines to modern construction, reinforces the ongoing human quest to understand and harness the physical world, continually adapting and innovating to overcome challenges.
Okay, once we understand the materials and the ingenious ways humanity has shaped them, we have to talk about the rules of the game. Building codes.
Ah, yes, the codes.
They might seem bureaucratic, but they're essential for safety, efficiency, and even protecting our investments. From fire resistance to wind loads, these codes are the unsung heroes of urban stability, codifying centuries of lessons learned.
Absolutely. Our sources, particularly Building Codes Illustrated, reveal that codes are not just arbitrary regulations. They codify probabilities and observations accumulated over generations, providing uniform standards for safety.
So they're based on real-world experience.
Exactly. They guide everything from structural fire ratings to ventilation requirements, and even how we account for forces of nature like wind. This is critical thinking applied at a societal scale, ensuring that the structures we inhabit can withstand foreseeable challenges, reflecting a continuous process of problem solving.
So these codes are literally built on lessons learned, often the hard way, about how buildings fail or perform under stress. What are some of the key safety issues they address?
That's right, they're a distillation of experience. Take fire resistance, for instance. Structural members and assemblies must comply with specific fire resistance ratings, and supporting structures must have at least the same rating as the assembly they support.
Makes sense.
Critically, service elements like pipes or conduits are prohibited from fire protection coverings because they can conduct heat, potentially compromising the rating.
Oh, that's a detail you wouldn't necessarily think of.
Right. Even interior floor finishes, especially carpets, are classified into Class 1 or 2 based on radiant flux tests to assess their flame spread resistance, with specific requirements for stairways, ramps, and corridors. These aren't just suggestions. They are mandates born of extensive research into how fire spreads and impacts building integrity, directly influencing design and material choices.
And what about the exterior of a building? It's constantly exposed to the elements and also plays a crucial role in preventing fire spread between buildings.
Great point. Exterior walls have stringent criteria related to property lines, openings, and projections. For example, combustible water-resistive barriers on Type IV construction over 40 feet in height must pass NFPA 285 testing.
NFPA 285. What is that test?
It's crucial for addressing concerns about vertical and lateral flame propagation on the exterior of tall buildings, preventing a fire from rapidly engulfing a structure.
Got it. Okay, what about roofing?
For roofing, underlayment, typically 15 or 30-pound building fill, is required to protect against precipitation and provide a second layer of defense. In very cold climates, an ice and water shield is mandatory beneath the roofing material to prevent water damage from ice dams.
Ice dams, right. Big problem in cold places.
Huge. Insulation placed between the deck and membrane, while common, must be carefully managed to avoid moisture problems and blistering, which can lead to decay and membrane rupture. Flashing is also essential at roof chimney intersections, often with counterflashing and a cricket.
A cricket, like the insect.
No. It's a small peak structure is needed on the upslope side of wide chimneys to shed water efficiently.
Ah, okay. Learn something new. So it's not enough to just keep the building standing and fire safe. It needs to be healthy and comfortable for its occupants too.
Indeed, ventilation is a key concern. In extremely cold climates where energy loss is a factor, ventilation openings to the interior are necessary. Crawl spaces, for instance, may require mechanical ventilation at a rate of 1.0 cubic foot per minute for every 50 square feet, especially if a vapor retarder covers the ground surface.
Specific requirements there.
Very specific. For flood hazard areas, ventilation openings must meet specific flood opening requirements to allow water to equalize pressure during a flood. Standards like ASHRAE 62.1/2010 provide a framework for effective ventilation, even recommending CO2 monitoring to optimize rates and save energy.
CO2 monitoring, interesting.
And finally, buildings must be designed to withstand wind loads from any horizontal direction, with particular attention to higher pressures at corners and roof edges. Structural members and cladding must be anchored to resist overturning, uplift, or sliding, with continuous load paths extending all the way to the foundation.
A continuous path down to the ground.
Absolutely essential. These codes are a living document of our collective understanding of how to construct durable, safe, and resilient environments, and they are constantly evolving as new insights and materials emerge.
Okay, looking to the future now. The concept of green building isn't just a trend, it seems like a necessity. Our sources show how integrated design and material choices are becoming central to creating structures that perform better for both people and the planet.
Yes.
This feels like a modern reinterpretation of that ancient idea of form and function working together, but with a global consciousness.
That's an astute observation. This shift towards sustainable construction absolutely reflects a deeper understanding of systems, how a building interacts not just with its immediate environment and its occupants, but with the broader planetary ecosystem and its entire life cycle.
The whole life cycle.
Exactly. It's about optimizing performance, from energy use to indoor air quality, and recognizing that decisions early in the design process have cascading effects throughout the building's life and beyond. This is where critical thinking truly becomes systemic, encompassing environmental, social, and economic factors, pushing us beyond mere aesthetics to holistic functionality.
So it's about building smarter, not just greener, and making sure we have robust ways to measure that intelligence and impact.
Precisely. Performance assessment methods like BREEAM have been instrumental in mainstreaming green building practices. They've broadened the scope of design considerations, moving beyond just new office buildings to cover hotels, factories, homes, and even commercial interiors or renovations.
So it's much broader now.
Much broader. This focus has expanded even further with tools like LEED-N, BREEAM Communities, and CASB Urban Design, which are now being applied to urban design and infrastructure planning. This indicates a growing need to redefine the spatial and temporal boundaries of what we consider in design, linking individual building performance more explicitly with its ecological and physical context, understanding a building as part of a larger living system.
And a major driver for this, of course, is energy. Our buildings consume a huge amount of it, and optimizing that feels like a direct evolution of the efficiency goals we've seen throughout architectural history.
Absolutely. Our sources confirm that energy use in U.S. buildings has been dropping, with standards like ASHRAE 90.1/2010 pushing consumption significantly lower through improved insulation, glazing, and HVAC systems.
So progress is being made.
Definitely. High-performance buildings allow for a significant downsizing of the mechanical plant and dramatically reduce capital costs. Life cycle cost, LCC analysis, is key here, enabling designers to optimize a building's energy consumption over its entire lifespan by considering upfront costs against long-term operational savings.
Thinking long-term.
Yes. Integrated design, which fully explores energy system optimization, can reduce construction costs and shorten schedules. For example, involving general contractors early in planning can streamline processes and identify cost-saving efficiencies, proving that collaboration is as vital as the technology itself.
But it's not just about energy. The materials themselves play a huge role.
Right.
Not just in their structural properties, but in their environmental footprint.
Indeed. Material selection now focuses intensely on high recycled content, reused materials, local availability to reduce transportation emissions, certified wood products, and rapidly renewable resources.
Lots to consider.
There is. And what's particularly promising is the emergence of environmental product declarations, EPDs, and environmental building declarations, EBDs. These are being developed as nutrition labels for materials and whole buildings, respectively.
Nutrition labels for buildings. I love that.
It's a great analogy, isn't it? It allows for objective comparisons and trade-offs to minimize total environmental impact. Interface Floor Corporation, a carpet tile manufacturer, is noteworthy as an early adopter, committed to obtaining third-party validated EPDs for all its products.
That's encouraging.
Ultimately, these declarations will enable whole building assessments, allowing us to compare the impacts of, say, additional insulation and triple-pane windows against a reduced HVAC system. This holistic approach supports more informed decision-making by prioritizing overall environmental performance. It kind of echoes Viollet-le-Duc's quest for structural honesty by demanding transparency about a building's ecological truth.
That's a fantastic connection. And it extends to the well-being of the people inside the buildings too, not just the planet. This sounds like an embrace of our fundamental human needs within these engineered spaces.
Exactly. Indoor environmental quality, IEQ, is a critical component of sustainable design. This includes integrating lighting, daylighting, and views, recognizing that good lighting design is crucial for human health and productivity, even though lighting consumes about 30% of total U.S. energy.
30%. Wow.
Yeah, it's significant. The concept of biophilia, articulated by the renowned biologist Edward O. Wilson, isn't just about preferring nature. It suggests an innate evolutionary craving for connection with the natural world, crucial for our well-being.
Biophilia.
Yeah.
So bringing nature in helps us.
Demonstrably. This is why incorporating natural light, views to the outside, and even natural materials into building design isn't just aesthetic, it demonstrably boosts human health, mood, and productivity.
Makes perfect sense.
Beyond visual comfort, IEQ also encompasses thermal and acoustic comfort, and even considerations around electromagnetic radiation and sophisticated HVAC systems. It's a comprehensive approach to creating spaces that are not only efficient and structurally sound, but also profoundly beneficial for those who live and work within them, making the building a truly integrated system for human flourishing.
Okay, let's shift gears slightly. Building isn't just about grand architectural statements or the science of materials. It's about meticulous planning and flawless execution on the ground.
Right, the doing part.
Exactly. Our sources delve into the world of project management, revealing the tools and strategies that keep mega projects on track. This is where the abstract ideas of design meet the concrete realities of getting things built, a testament to organized human ingenuity.
This is where we see the sophisticated application of structured thinking to complex real-world endeavors, whether it's the detailed planning outlined in the PMBOK guide or the specific scheduling techniques like the critical path method or CPM.
CPM, yeah.
Effective project management is about minimizing uncertainty, managing risk, and ensuring stakeholder alignment. It's about building a predictable path in an often unpredictable environment, especially in construction where so many variables, from weather to material supply, are always at play. It's a continuous process of problem solving.
So it starts with a clear roadmap, defining what needs to be done, by whom, and when, almost like orchestrating a massive, multifaceted organism.
Precisely. Project planning guides the project work, the delivery of outcomes, and the ultimate business value. Project teams and stakeholders establish clear measures of progress and success, and performance is constantly compared against these initial plans.
But things change, right?
Always. Because construction inherently involves uncertainty, plans are dynamic. They're revised or new ones developed as events or conditions emerge. Long-term goals identify the intended value, and risk thresholds are defined from the outset, influencing how potential issues are managed. It's about proactive adaptation.
I've heard of the critical path method, or CPM. How does that fit into this detailed planning and what makes it so critical?
CPM is a fundamental scheduling technique that helps identify the sequence of activities that dictates the shortest possible project duration. It involves defining activity durations, typically in working days or hours, and identifying milestones.
Milestones. Those are like checkpoints.
Exactly. Zero duration activities marking important points of interest, like the project's start or finish. A crucial component is the precedence diagram, which visually represents the sequence of activities and their interdependencies. From this, we can determine the earliest start and finish dates for each activity.
Okay.
A key concept derived from CPM is total float, TF. This is the number of days an activity can be delayed without delaying the overall project duration.
Ah, the wiggle room.
That's a good way to put it. For instance, if an activity has a TF of 3 days, it means it can be pushed back 3 days without pushing back the project's end date. However, using float on one activity can reduce the float available to subsequent activities, so it needs careful management to avoid unintended ripple effects through the schedule.
That makes incredible sense. It's all about balancing flexibility with the overall project timeline. What about the contractual side of things and keeping everyone on the same page, especially given the sheer number of contractors and subs involved in a large project?
Contracts play a significant role in managing financial and operational aspects. Unit price contracts, for example, base payments on precise measurements of field quantities, which can lead to overall cost deviations if actual quantities differ from estimates.
Potential for surprises there.
Can be. Lump sum contracts, on the other hand, offer a more precise final price from the start. Another crucial aspect is submittals. These are documents like shop drawings, product data, or samples submitted by the contractor for review and approval by the design team to ensure conformance with contract documents.
So checking everything aligns.
Vital for coordination and quality control. Our sources also emphasize that once a baseline schedule is published, it becomes the official project roadmap. Any changes to activity sequences or time allotments must be rigorously documented. For example, through a request for time extension or a proposed change order to formally acknowledge delays and their associated costs. This ensures transparency and accountability.
So it's a continuous process of communication and adaptation, supported by clear documentation. And there are even dedicated structures within organizations for this, aren't there? Almost like institutional memory for project success.
Yes, project management offices, PMOs, are often established to strengthen future project delivery. They achieve this through continuous improvement, facilitating knowledge transfer from completed projects across the organization and managing change.
Learning from the past.
Exactly. By sharing project results, PMOs inform strategic and business objectives, building alignment with process updates and new skills. This institutionalizes learning and ensures that valuable insights gained from one project benefit all subsequent ones, creating a cycle of continuous improvement. Effective project management is truly about bringing order, foresight, and adaptability to inherently complex undertakings, much like a good conductor leads an orchestra.
Okay, but what happens when the building itself becomes intelligent? The rise of building information modeling, or BIM, is fundamentally transforming how we design, construct, and even operate buildings.
BIM. Yes.
It's not just a software update. It feels like a whole new way of thinking about the entire life cycle of a structure. Maybe even a digital evolution of that structural honesty Viollet-le-Duc so admired.
That's a profound connection. BIM truly represents a paradigm shift, moving far beyond traditional 2D drawings. As our sources emphasize, BIM is not just a technology change, but also a process change.
Process change, okay.
It represents buildings using intelligent objects that carry detailed information about themselves, their materials, dimensions, properties, even their cost, and understand their relationships with other objects within the model.
Intelligent objects.
Yes, this isn't just about efficiency. It's about enabling entirely new capabilities, fostering unprecedented collaboration, and allowing for a level of precision that was previously unimaginable. It's a key part of what some call the third digital revolution in fabrication, allowing us to connect the realities of bits and atoms in ways never before possible, making the entire building a single, cohesive digital system.
So these intelligent objects contain rich data that informs every stage of a project. That sounds like it streamlines a lot of previously fragmented processes, bringing a new level of coherence to design and construction.
It dramatically alters all key processes, bringing that coherence to the forefront. From capturing client requirements and developing space plans to analyzing design alternatives for aspects like energy performance, structural integrity, cost, and constructability, BIM integrates it all.
Everything connected.
Right. It facilitates multidisciplinary collaboration, both within a single discipline and across multiple ones, like architecture, structural engineering, and mechanical systems. In construction, it supports the precise fabrication of components by subcontractors, and post-construction, it aids in facility operation and maintenance by providing a digital twin of the building. BIM brings greater intelligence and efficiency to each of these stages, making the building's logic transparent and accessible.
What are some of these new capabilities that BIM enables beyond just better drawings?
One significant capability is conflict detection, often called clash detection.
Clash detection, right? Finding problems early.
Exactly. It identifies unintended material or system interferences in a 3D project model before construction begins. Imagine finding out a pipe is slated to run directly through a structural beam. BIM catches that in design, saving immense time and cost by avoiding on-site rework.
Huge savings potential.
Massive. BIM can also enable automated design changes, for example, quickly rerouting mechanical equipment in response to a detected clash. The detailed data within BIM models supports data-driven handover processes, such as using COBie-2.
COBie-2?
Construction operations building information exchange. It allows for seamless integration with computerized maintenance and management systems, CMMS, like Maximo, providing facility managers with immediate access to crucial building information.
So the data lives on after construction.
Precisely. Furthermore, fully coordinated BIM models allow for the isolation, analysis, and optimization of project areas, creating significant opportunities for prefabrication, where components are built off-site under controlled conditions, further increasing efficiency and quality.
That sounds like a dream for collaboration, but what about ensuring all these different digital systems and teams can actually talk to each other without losing crucial data? That seems like a challenge.
It is a challenge. That's where interoperability comes in, and it's absolutely fundamental to BIM success. Exchanges between BIM platforms and various analysis tools for structural analysis, thermal performance, quantity takeoff, scheduling, and procurement are critical.
So how do you make that work?
Model view definitions, MVDs, are crucial here. They define precisely what information should be expected for an exchange to be effective, aligning export and import processes and eliminating mismatches in assumptions.
Like a common language translator.
Sort of, yeah. This ensures that when, for example, an architect's model is shared with a structural engineer, both parties have clear expectations of the data contained and its format. The goal is to define effective exchanges to smooth and expedite workflows, enabling the seamless flow of intelligent information across the entire project lifecycle, embodying a truly systemic approach to building.
And who takes responsibility for managing all this intelligence? It seems like it would require a new level of coordination and active involvement from the building owner.
It absolutely does. BIM potentially requires insight across multiple organizations and project aspects. This demands more direct owner involvement and clear roles and responsibilities due to the increased fluidity and interactivity of the process.
Owners need to be more hands-on.
Yes, owners need to be prepared for ongoing participation as issue discovery and problem identification occur earlier and more frequently in the design phase. This shift emphasizes managing the model itself as a critical project component, ensuring that the benefits of BIM-like early issue resolution and better life cycle data are fully realized, rather than being seen as a drawback due to increased owner engagement. It's a testament to the idea that a truly intelligent building requires intelligent collaboration from all stakeholders.
Okay, but with all this talk of technology and systems, it's easy to forget the people involved.
The human element. Crucial.
Right. Our sources remind us that the nature of work itself is changing, from the hands-on craft to the complexities of digital collaboration. What does it mean for individual agency and the very experience of work in this evolving landscape?
This highlights a crucial tension: the quest for efficiency and integration versus the individual's experience of work. When we talk about digital revolutions or system design, we must remember that it impacts the morale, productivity, and even the sense of purpose for those doing the work.
Yeah.
Our sources, like Matthew Crawford's Shop Classes Soulcraft, eloquently describe a growing sense that the official story we've been telling ourselves about work is somehow false, particularly in white-collar office environments. It forces us to ask what value is being created and by whom.
It sounds like beneath the rhetoric of teamwork and metrics, there's a significant tension, almost a loss of individual agency and objective standards in modern work. What are the practical consequences of this mismatch between form and content for morale or innovation?
That's a profound way to put it. Crawford argues that the proliferation of contrived metrics and the rise of teamwork can make individual agency elusive, making it incredibly difficult to trace individual responsibility or objective contribution.
Hard to know who did what.
Exactly. This contrasts sharply with the tangible, undeniable results of, say, a carpenter's level or a well-joined piece of stone where the standard is objective and immediately apparent. Managers themselves can find their roles bewildering, sometimes appearing as therapists or life coaches, while navigating vague imperatives. This can, unfortunately, create a Potemkin meritocracy, where one's personality or affable complacence seems to matter more than actual knowledge or hard work, fostering a genuine mismatch between form and content in modern work that can profoundly erode morale and stifle true innovation.
That's a profound observation about the changing nature of white-collar work.
Uh-huh.
But what about the physical crafts, the actual making of things, which Viollet-le-Duc so admired in the medieval masons? Has that changed too?
It has changed dramatically, and Viollet-le-Duc would have much to say about it. Joseph Moxon's Mechanic Exercises offers a fascinating glimpse into highly specialized 17th century craft work like type founding.
Type founding, making letters for printing.
Exactly. He describes the meticulous process of filing punches, justifying matrices, and bringing letters to their true fatness with small files. This was work demanding immense skill, precision, and an intimate understanding of the material.
Real hands-on skill.
Absolutely. This contrasts starkly with modern mass production and prefabrication. For example, the book House describes carpenters installing pre-hung doors, already hinged to jambs, a process that takes some tinkering, but there's nothing very interesting in it for the craftsman, often reduced to patching holes for improperly prepared knobs.
Also less skill involved, maybe.
Less of that deep integrated skill. This shift from bespoke creation to assembly line components has profound implications for the craftsman's role, leading to a potential loss of that deep, integrated understanding of structure and form that Viollet-le-Duc saw in Gothic builders.
So the hands-on connection to the material and the individual's mark on the final product seem to be diminishing in many areas, even as our buildings become more complex and digitally integrated.
Indeed. It forces us to consider the cyborg condition mentioned in The City of Tomorrow, where digital technologies become a dynamic extension of our bodies and minds, demanding constant and two-way cybernetic exchange.
That's cyborg condition.
This blurring of human and machine impacts how we work, blurring the lines of what is human effort versus technological augmentation. The meticulous individual craft, where each stone was finished before being laid in medieval cathedrals, as Viollet-le-Duc so admired, gave way to a system where ornament was cut in place, diminishing the mason's understanding and skill.
Right.
Now, with digital fabrication, we are seeing a new kind of precision and efficiency emerge. But it critically raises questions about the role of human agency and craftsmanship in a deeply interconnected, technologically augmented workflow. How do we ensure that in our quest for efficiency, we don't lose the soul craft of building, or the profound human satisfaction that comes from mastering a material and seeing its honest expression in the final form?
That's a really important question. Okay, so what does this all mean when we put it all together? Our world is a vast, interconnected web, and understanding how these systems behave is critical. Our final section is a deep dive into systems thinking itself, offering lessons that apply to everything we've discussed today.
Yes, from ancient architecture and rational Gothic structures to modern management and BIM.
Exactly.
This is where we truly synthesize the various threads we've pulled. Donella Meadows' seminal work, Thinking in Systems, makes it clear that fundamentally, there are no separate systems. The world is a continuum.
No separate systems.
There are only boundaries of word, thought, perception, and social agreement, artificial mental model boundaries. This perspective challenges our innate human tendency to segment and simplify the world into discrete problems, a tendency that often leads to unintended consequences when we try to intervene in complex systems. It's about recognizing the hidden connections.
That's a powerful point. We draw boundaries for convenience, but they don't necessarily reflect how things truly operate in reality. This must mean that interventions often have unexpected and sometimes counterintuitive results.
They frequently do. Systems often behave counterintuitively, defying simple cause and effect reasoning. Meadows offers a striking example. Acting faster makes the oscillations worse.
Acting faster makes things worse.
Can do, yeah. Shorter reaction times in a system rather than solving problems can actually exacerbate them, creating more instability. She talks about pulling a high leverage lever in the wrong direction and creating perverse results.
Wow.
This is why a shift from an illusion of control to a stance of listening and adapting is so crucial. We need to acknowledge that the future can't be predicted, but it can be envisioned and brought lovingly into being. Systems can't be controlled, but they can be designed and redesigned. This lesson applies across all the domains we've covered, from designing a building that truly integrates with its environment, expressing its structural logic, to managing a complex construction project with adaptive planning.
So we need to understand the underlying structure and dynamics of these systems to identify where real, effective change can happen, rather than just reacting to symptoms with quick fixes.
Exactly. The concept of hierarchical systems is also important here. Within these systems, relationships within subsystems are denser and stronger than relationships between them.
Okay.
If these differential information links are designed correctly, feedback delays are minimized, and no level is overwhelmed with information, allowing the system to work with efficiency and resilience. This is similar to how a well-designed building's structural components work together at different scales.
Right, like the building itself.
And crucially, Meadows points out that the purpose of the upper layers of the hierarchy is to serve the purposes of the lower layers. A profound insight into how organizations and communities should ideally function. Many relationships and systems are also nonlinear, meaning small changes can have disproportionately large or small effects, making prediction difficult and demanding a more humble, adaptive approach.
Can you give us an example of a leverage point that might seem incredibly counterintuitive, something that makes us fundamentally rethink our assumptions?
Certainly. Meadows described how the world model, developed by Dennis Meadows and his colleagues, when asked to solve global problems like poverty, hunger, and environmental destruction, identified growth, both population and economic, as a key leverage point.
Growth. But isn't growth usually seen as the solution?
Exactly. That's why it's so profoundly counterintuitive. The model revealed that growth has costs as well as benefits, and we typically don't count the costs. These uncounted costs often are the problems we're trying to solve with more growth.
So the solution is part of the problem.
In many ways, yes. What is needed then, according to the model, is not just unbridled growth, but much slower growth, very different kinds of growth, and in some cases, no growth or negative growth. This demonstrates how systems thinking can reveal profound truths, prompting us to question our deepest assumptions and seek interventions that genuinely align with the system's true behavior, rather than simply pursuing our desired outcome without understanding the broader consequences. It's a powerful lesson in critical thinking applied to our entire world system.
Okay, if we embrace systems thinking, recognizing these interconnected loops and counterintuitive behaviors, what kind of future can we envision for our built environment? Our sources introduce us to futurecraft.
Futurecraft, yes.
The idea that we can actively shape our urban environments, turning buildings into intelligent agents and communities into centers of innovation. It sounds like an exciting, proactive vision.
It is. This vision suggests a profound shift towards what the city of tomorrow calls living architecture, where buildings become dynamic interfaces, capable of learning from and coexisting with occupants.
Learning from occupants.
Exactly. It's about leveraging ubiquitous sensors and digital fabrication to create responsive spaces and foster urban self-sufficiency, fundamentally connecting the realities of bits and atoms. This is a deliberate, collaborative process, moving beyond passive structures to active participants in our lives and environments, always learning and adapting.
This sounds like a logical next step from BIM, taking digital modeling to a whole new level of interactivity and responsiveness, where the building itself becomes a constantly evolving intelligent system.
It is, absolutely. This represents what the authors call the third digital revolution, following communication from analog phones to the internet and computation from personal computers to smartphones. This revolution is in digital fabrication.
Making things digitally.
Right. Fab labs, for example, are emerging as key centers for production, learning, and community building globally. They accelerate self-sufficiency by allowing communities to collaboratively produce goods, from food to furniture, leveraging digital tools.
Local production.
Exactly. This decentralizes production, moving it out of the factory and returning to a local and user-centric model, potentially leading to new domestic typologies that combine dwellings with fabrication, recalling medieval artisan shophouses or cottages.
Like Villa's skilled medieval craftsmen, but with new tools.
That's a great connection. It aligns surprisingly well with the spirit of skilled medieval craftsmanship that Villaduc so admired, where local artisans understood the entire process from material to finished form, but now augmented by digital precision.
So imagine a future where your house isn't just a static box, but a dynamic entity that understands and responds to you and its environment and maybe even helps you make things. That's a truly transformative idea.
Precisely. Living architecture envisions buildings transforming into intelligent agents with the capacity to learn from and coexist with their occupants, creating dynamic spaces and interfaces. This means buildings could actively participate in optimizing comfort, energy use, and even health, using sensor networks and communication systems. The goal is to facilitate as seamless a movement as possible from fast to slow, virtual to physical, cerebral to sensual, automatic to manual. It's about the built environment becoming a connective tissue between our digital and physical realities.
It's not just top-down smart cities, right?
No, and that's crucial. It's also about citizen empowerment. Forums for participation allow citizens to engage in collective action and transform their surroundings. As the city of Tomorrow states, there can be no smart city without smart citizens, emphasizing the need for bottom-up actions and collaborative futurecraft at the intersection of the digital and physical worlds. It's about designing systems for people, by people, with an intelligent understanding of how everything connects.
What an incredible journey.
Yeah.
From the structural honesty of ancient Greek temples and Viollet-le-Duc's meticulous analysis of Gothic cathedrals as rational structural systems, to the intelligent objects of BIM and the broad strokes of urban futurecraft, we've seen how deeply interconnected the past, present, and future of our built world truly are. It's a powerful lesson in learning from history, not by copying its style, but by understanding its logic, and then applying that logic in new, innovative ways. We've certainly pulled out some incredible nuggets of knowledge today, highlighting the timeless human quest for ingenuity and efficiency.
Indeed. This deep dive into these diverse sources reinforces the idea that true innovation often comes from synthesizing knowledge across fields, recognizing patterns, and adapting principles. The constant evolution of how we design and build, from early Roman engineers to Viollet-le-Duc's rational Gothic insights and to modern BIM specialists, fundamentally boils down to a continuous process of problem-solving and critical thinking. It's about striving for greater efficiency, honesty, and structure, and ultimately better performance for both people and the planet, constantly pushing the boundaries of what's possible through a deeper understanding of systems.
And for you, our listener, this means that every building, every city block, every piece of infrastructure around you is a testament to centuries of trial, error, and ingenious solutions. The next time you walk through a bustling city or admire an old structure, perhaps you look at it not just for its appearance, but for the underlying systems and principles that hold it all together.
The invisible logic.
Exactly, the invisible logic that makes it stand, function, and even thrive. Makes you wonder, doesn't it? What invisible principles, currently being explored in one niche, will become the foundational logic of our world 100 years from now? Much like Viollet-le-Duc's profound insights into medieval cathedrals echoed through the modern era, shaping our very approach to design and construction.